Welcome to the next calculus video. In this one, we're going to do section 2.2, basic differentiation rules and rates of change. A big section in the book here. We're going to find derivative of a function with the constant rule, and that will lead us to the power rule, and then the constant multiple rules, the sum and difference rules, derivatives of sine and cosine, and we'll get to the other ones later in the book. Find the derivative of exponential functions and derivatives as rates of change. We are going to get to these rules. We could call them shortcuts, easier ways to take derivatives than the difference quotient that we have been using. So here, let's get this out of the way. First, the constant rule. In the last section, we used the limit definition to find derivatives. In the next two sections, we're going to be introduced to several differentiation rules that allow us to find derivatives without direct use of this limit definition. And remember, we had a rule something like this, the limit as x approach. I'm just going to put 3 in there of 7. Remember, this is our function, the 7, y equals 7. If we graphed it, it would be a horizontal line with a y height of 7. And any constant function like that is going to have a 0 slope. Remember, derivatives are about finding slopes. The derivative of any constant function is always going to be 0. It sounds easy, but I'm sure to trick up a few of you in class. Let's just take a look at these here. Example 1, we have a function, we want its derivative, y equals 7. So let's do a dy dx for our notation. That derivative would be 0. Here's our function f of x. f of x is 0. The derivative f prime of x would also be 0. Here's s of t is negative 3. Well, let's write this one as ds dt. The derivative of s with respect to t is equal to 0. Now, if I trick you with, it's going to be something like this. You're going to get used to a future rule, and you're going to want to start playing with exponents and finding a derivative a different way here. K is a constant, pi is just a number, and you're squaring that pi. You know, it's weird looking, but this is just a constant. So our y prime, our derivative is going to be 0. The derivative of a constant is nothing. Okay, before we get into this power rule, let's talk about expanding a binomial. Well, first, you know, our limit definition of a derivative, our delta x is going to head to 0. The numerator was f of x plus delta x. And then in a lot of the examples, I switched to red ink and wrote minus f of x, and this was over delta x. And then we got to a point in the problem when we did some algebra here and maybe foiled out the red part, and we subtracted the original function. Everything here in red, even if there was several terms, would always cancel with some of the stuff over here. And then all the remaining terms had a delta x that we canceled with the denominator delta x. And then we could let our limit go to 0. So and we're just going to focus here just on this numerator part. F of x plus delta x minus f of x. So again, this part, every term canceled with something over here, and then a delta x would divide out. Let's think back to binomial expansion. Remember Pascal's triangle. We start with a 1, and a 1. And if we continue the triangle edges down, this would be a 1 and this would be a 1. But if we add the numbers in the middle, we get a 2. And we continue down the edges of the triangle 1 and 1. Here the 1 plus 2 is 3. 2 plus 1 is also 3. One more level, 1, 1. 1 plus 3 is 4. 3 plus 3 in the middle is 6. 3 plus 1 is 4. These are the coefficients of our expansions of, I'm just going to write this as x plus y. Here's x plus y to the first. There's a 1 in front of the x and a 1 in front of the y. But if we did x plus y squared, we would have x squared plus 2xy plus 1y squared. And if we did the x plus y quantity cubed, we would also have the 1, 3, 3, 1, and then we would come up with our exponents in there. And actually, I should have been writing it like this when we get to this one. So if this was part of our difference quotient, we would have an x squared, and these would be expansions for, let's do for x plus delta x. So there would be a 2x delta x plus a delta x squared, and then I don't have room for it, but we would minus the original x squared, and that would wipe out this first term. It would be gone. In our next expansion, that would be x to the third plus 3x to the second delta x to the first plus 3x delta x squared, and then our constant, and then we would have a minus x cubed. So over here, and again I don't have the full expansion, would be a minus x cubed that would cancel this leading term. So this leading term gets canceled out. For this one, we would start out with, this would be fourth power, so that would be x to the fourth plus 4x cubed delta x to the first. And then we would have 6x squared delta x squared also. But way at the end of this, we would have a minus x to the fourth that would cancel out this leading term. So that's always happening. We cancel out the leading term. And then remember, in our difference quotient, our denominator is divided by delta x. So this here, I'll put in black parenthesis, this delta x would get divided by delta x, so that would turn into a 1 and become irrelevant. Same thing down here, we have this 3x squared, delta x to the first, that would get divided out. Down here, 4x cubed, delta x to the first, that would get divided out. And then any term coming to the right of these would have at least a delta x left in it, even after we cancel with the denominator. This delta x squared is now delta x to the first, and it would be true for any term after these would have at least a delta x left on them. So when we applied our limit and we let delta x go to 0, all those other terms are going to disappear. So let me switch. I think I haven't used green ink yet. So when we have the expansion for that quantity squared, we're left with this term, 2x. For the third power one, we have 3x squared. For the x to the fourth, here are the leading term that remains is 4x cubed. Do you see the pattern? Have you noticed the pattern to it yet? If I can clear a little space here in between. Here the function would have been, x squared. The derivative is 2 times x. Here is x to the third, derivative 3x to the second. Function x to the fourth, derivative 4x to the third. The exponent comes down in front. You lower the power by 1. And here it is written in our calculus notation. The power rule. If n is a rational number, then the function f of x equals x to the nth power is differentiable, and I'm going to just rewrite it here, d dx, the derivative with respect to x of x to the nth power is, bring down the exponent, n. Now you're going to multiply that by x, and whatever this exponent was, n, you're going to subtract 1 from it. That's your new exponent. Bring your exponent down, keep the base x, subtract 1 from the exponent. So if I ask you for the derivative of x to the 12th, with the old definition, you'd have to do x plus delta x to the 12th power, and binomial expansion on that. That would take a very long time. But with the power rule, the derivative of x to the 12th is 12x to 1 power lower to the 11th power. Beautiful, beautiful mathematics. For f to be differentiable at 0, n should be a number that the x to the n minus 1 is defined on an interval containing 0. Now, the book says when using the power rule for which n is 1, they say just think of it as a different case. The derivative of x is equal to 1. They just want you to memorize it. This also follows the rules of, the power rule. If I have x to the first and I want to derive it, I would bring the exponent down front, so it would be 1 x to 1 power lower, x to the 0. What is x to the 0? Well, anything to the 0 powers 1, so your answer is just 1. I don't see it as a special case. It's just another use of the power rule. Oh, and that's consistent, if you think about this graphically, y equals x. That's just a straight line, slope of 1 going through the origin. So the derivative of that should be 1. All right, let's take this new power rule for a test drive. F of x is x to the third. F prime of x is going to be, bring the 3 down, keep the base x, drop the exponent by 1, 3x squared. It's just that easy. Now this one, before we derive it, let's write it with a rational exponent. That would be x to the 1/3 power. That's supposed to be a 3, you get the idea. So here g prime, our derivative, we're going to bring the exponent down front. Now it's going to be 1/3 x. Now we got to drop the exponent by 1. 1/3 minus 3/3 is negative 2/3. Now, it's bad manners to leave negative exponents in your answer. So here, the x with the negative 2/3 exponent is going to jump down there in the denominator with that 3. This 1/3 has its own exponent. That's 1/3 to the first power. So it's staying where it's at. X to the negative 2/3. That x to the negative 2/3 will join the 3 in the denominator, where the exponent becomes positive. Letter C, we've got y equals 1 over x squared. We could rewrite 1 over x squared as x to the negative second power. And now let's derive y, dy dx, the derivative of y with respect to x. Bring the 2 down front. Now it's a negative 2 coefficient. We've got our base x, and we drop our exponent by 1. It gets more negative, down to negative 3. The negative 2 has an exponent, so let's get rid of the x to the negative third. It's going to jump downstairs, become x to the positive third, and there's our answer. Negative 2 over x to the third power. Now what's this down here? Oh yeah, in that 2c, note that before we derived this function, we rewrote it with a negative exponent. Rewriting is a first step in many differentiation problems. Oops. So let's try this out here. We did an example like this before when we were first learning derivatives with the difference quotient. Now it'll be much easier with our new power rule. Find the slope of the graph of f of x equals x to the fourth at these x values. So x to the fourth, this would be negative 1 comma 1, 0, 0, and 1, 1. We're going to find those slopes. But first we need a derivative. Here is our position function. F of x is x to the fourth. X's go in and y values come out, and we can locate our position in the plane. F prime of x is our derivative. Bring down the 4, keep the x, drop the exponent by 1. This is our slope function. X's go in, slopes come out. So f prime at negative 1 would be negative 1 cubed is negative 1 times 4 is negative 4. F prime, they asked us at 0. That would be 4 times 0 cubed, or 0. And finally, f prime at positive 1. 4x to the third, that'd be 4 times 1 cubed, or positive 4. So we can see on the graph what we just found there with our function. At negative 1, this point, the negative 1 goes in the original function, we get the y value 1, but we put that into the derivative, that same x value, and this slope, the slope of that blue tangent line there is -4. We put 0 in the original function and out pops a 0. That's our location in the plane. 0 in the derivative gives us a 0-sloped tangent line. Put 1 in the original function, you get the point 1, 1. Put that same 1 in the derivative, you get the slope occurring at that point. The slope is +4. So the derivative function is another function that gives us the slope anywhere we want on the original function. Example 4. Find the equation of a tangent line. So when we're done, we want the equation of a line y equals mx plus b. And remember, the big idea here is to come up with the equation of a line, we need two things. We need a point. That's supposed to be an n. We need a point, and we need a slope. Ooh, and well, they gave us an x value, so we've got half of the point. -2 is our x value, and our function is x squared. We don't have the slope just yet. So let's see. If I put the -2 back in the original function, -2 squared is 4. So we've got a point. Slopes, we find slopes with derivatives in calculus. F of x is x squared. Our derivative function will be f prime 2 times x. So we've got a slope function. Our x value of interest is -2. F prime at -2 is 2 times -2 and -4. So we've got our slope, -4. All right. We can now come up with our tan line. Y minus y1 equals m quantity x minus x1. And we plug in the stuff we have. Y minus 4 equals slope -4 times x minus -2. Minus the negative will turn that positive. So over here, we're going to have y equals distribute -4x. And when we distribute here, that will be a -8, but we're going to add 4 more. So that'll be -4. And it says here graphical solution. I can't remember if I left the graph in there. This is not a hard one to graph at all. We could come up with a decent graph if we need to. Yeah, let's even do our own graph. Parabola. The original equation is simple to graph. X squared, so 0 squared is 0, 1 squared is 1, -1 squared is 1. 2 and -2 would take us up to 2, 3, 4. So our parabola looks something like this. And now here's our tan line. I'm going to switch over to blue ink. -4x minus 4. So y-intercept is -4. -1, 2, 3, probably down here somewhere. And our point of tangency was at -2, 4. So I could draw my tan line here. It's point of tangency, and then it's going to cross the x-axis or the y-axis at -4. The book's graph will be a little bit better than mine. Maybe in class we can do one of these and graph the original function and also graph the tan line we come up with. So here's the better book graph. Point of tangency, and they don't have the y-intercept. That would also be off of their graph. Now the constant multiple rule. We can factor a constant out, take a derivative, and put the constant back in. So the theorem in the book says if f is a differentiable function, c is a real number, then c times f is also differentiable, and here in the notation, we're deriving with respect to x, c times f of x. So you could sort of mentally, we're going to bring that number c out. We can derive f into its derivative f prime, and then just put that constant right back in. So constants, we can multiply by these, and the rules still apply. Like, let's see here, example 5. Now, here's how the book would do this. To do it step by step, they're saying you could pull the 5 out. And then you would derive the x cubed. We would pull the 5 out and derive the x cubed into 3x squared. And then we could bring the 5 back in and multiply by the 3, and you get 15x squared. More efficient, when it's in this form, when we bring the exponent down, if there's a 1 there, that 3 will just take its place. But since there's already a 5, we just multiply them. So our derivative dy dx is we bring the 3 down, it hits the 5, and you multiply it to a 15x squared. Here you would sort of factor this 2 out and then derive the 1 over x and then multiply the 2 back in. Or we could just do it this way. This is our function, 2x to the negative 1. Instead of moving the 2 out and then bringing it back, let's just, when we bring this negative 1 down, this is going to be y prime. Negative 1 times 2 is negative 2. And then we have our x, but we drop the power by 1 down to negative 2. Remember, this negative 2 has its own exponent 1. So we are going to leave that negative 2 in the numerator. X squared will be in the denominator when we move that down. Now here, this one, 4t squared over 5, you could sort of mentally drag the denominator 5 out and make that a 1/5, and then you could bring the 4 out and make it a 4/5. Or you see that that we got a 4/5 right there times t squared. The easiest way probably to do this is think about it as 4/5 and drop the t off of there. So now we can just derive this with the power rule. This exponent squared is going to come down and multiply. 2 times 4/5 is 8/5. And then we're going to have t to 1 power lower. 8/5 t to the first. Y equals 2 square root x, or that's 2x to the half power. Derivative y prime is going to be, bring down the 1/2, multiply by the 2 that's there. Half of 2 is 1, x to 1 power lower. 1/2 minus 2 halves is negative a half. X to the negative half. And we don't want to leave a negative exponent, so the 1 will stay up in the numerator. X to the negative a half goes downstairs, denominator, where it becomes x to the positive half. Ooh, letter E looks fun. So down here in this denominator, cube root of x squared, that's just x to the 2/3 power. So it's x to the 2/3. Let's bring it up, though, and make it negative. And notice this 2 here is going to stay as part of a fraction. We have a 1 in the numerator. That 2 is downstairs. And we bring out the x to the 2/3. Now it's x to the negative 2/3. We've brought it up from the denominator where it was positive. So now it's time to derive dy dx. This exponent, negative 2/3, is going to come down and get multiplied by a half. So that's going to be what? Negative 2/6. And negative 2/6 is negative 1/3. And then we're going to have our base x. We got to drop the power by 1. We're at negative 2/3. We're going to minus 3/3 more. We can add the opposite. That's negative 5/3. And of course, leaving negatives and exponents is bad math manners. So this fraction out front, the negative 1/3, I can write like this. There's negative 1/3. But now this x to the negative exponent is going to hop down there in the denominator, where it becomes x to the 5/3, and it's down there with the 3. For this one, negative 3x over 2, or look at it as negative 3/2 x. Well, the derivative of x is 1, so x's just derive away. Or you could do the power rule, 1 times negative 3/2, this will be y prime. 1 times negative 3/2 is negative 3/2, x to 1 power lower, x to the 0. Anything to the 0 is 1, so we can just erase that and we've got a good answer. So now here's where the book starts doing this. The constant multiple rule added together with the power rule can be combined into a more powerful power rule. So here we've got this leading number c. When the n comes down, you just multiply it. C times n. And then we have our base x, and we've dropped our exponent by 1. Now here, using parenthesis when differentiating, we want to sort of, when we're playing around with these variables, or just to be aware of those grouping symbols, because if you look at a and b, they're similar. Here it's 2x cubed, here it's 2x quantity cubed. Down here, 3x to the negative 2. Here it is quantity 3x to the negative 2. So be cautious of these, and let's see how these are going to work out. The first one's not bad. In the rewrite column, we could just rewrite that as 5 halves x to the negative 3. Bring that denominator x third up. Now we're going to derive it. Multiply the exponent by the fraction that's there. Negative 3 times 5 halves is negative 15 halves. We'll have our base x, but it goes down one level to the negative 4th power. Now to simplify and make it pretty again, we're going to have our negative 15 halves, but x to the negative 4 will jump down in the denominator with the 2, where it will be x to the positive 4. Now letter B is pretty similar, but before we do anything else, let's expand that. 2x quantity cubed. 2x times 2x times 2x is 8x cubed. So now it's 8x cubed. So here, the difference from what I have above in the black ink, now it's just going to be that denominator's different. We are going to make it 5/8 x to the negative 3rd, just like we did above up here with 5 halves. Now we're actually going to do some calculus. We're going to derive it. Negative 3 times 5, that'll be negative 15/8 x to the negative 4. And we'll have our negative 15 over 8, and the x to the 4th will join it down there. Y prime equals, there's our derivative. Now letter C, 7 over 3x to the negative 2. We're just going to bring this x to the negative 2 out, and when it comes out from that denominator, it's going to change positive, x squared. So now this is just 7/3 x squared. 2 times the fraction will be 14/3 x to 1 power lower, just 14/3 x. And I'm going to label that dy dx. I don't know if it's a derivative or not unless you label it with some derivative notation. The last one, not just that quantity is, the 3x is in a quantity. Let's do the same thing. We're going to bring the quantity up, and we'll change that to a positive exponent. So there was a 7 in the numerator, but we're going to bring up a 3x, and its exponent will change sign to positive. So we haven't done any calculus yet. Let's FOIL this out. 3x times 3x will be 9x squared, and times this 7 in the front. 7 times 9 is 63x squared. So our rewrite is 63x squared. That's a terrible exponent. That's better. So now let's derive it. dy dx. Exponent 2 times 63, that's 126. Base x, but now it's 1 power lower, it's first power. So there's, be careful with derivatives. When you see some parenthesis, you might have to FOIL things out or expand them to make the deriving easier. There we got sum and difference rules. Here we go. The sum or the difference of two differentiable functions f and g is itself differentiable. Moreover, the derivative of f plus g or f minus g is the sum or the differences of their individual derivatives. So here, if we're taking the derivative of two functions added together, we could just derive the first function and then derive the second function and add them together. If we're subtracting them before we derive, we just subtract the derivatives after they're done. So this sum and difference stuff is pretty simple. When it comes to polynomials like this, we can just derive each term separately as we go. So let me move this over here. So our derivative f prime x, well, the derivative of the first term, x cubed, will be 3x to the second. The derivative of negative 4x is minus 4, and constants derive to nothing. So there's our derivative. Now this first one, oops, negative x to the fourth over 2, think of that as, there we go, negative 1/2 x to the fourth. We can have that x to the fourth sort of slide off of the fraction, leaving a 1 up there. So when we derive this, 4 times negative 1/2 will be, let's call this g prime, negative 2x to 1 power lower, negative 2x to the third. Derivative of the middle term here, 3 times 3 is 9, so that'll be a plus 9x to 1 power lower squared. Here at the end we have a minus 2x, so that will derive to a minus 2. The x will derive away, turn into an x to the 0. So just derive each term separately. Now this one. We will learn how to derive stuff that look like a fraction, a rational function. But for now, there's actually an easier way to do this. Notice our denominator is a single term, and our numerator is multiple pieces. Let's break it up. 3x squared will get its own denominator x. The middle term x will get its own denominator x, and the 1 on the end will get its own denominator x. Now we can simplify each piece. 3x squared over x, well, that's just 3x. Minus x over x is 1, and let's rewrite the last term 1 over x to x to the negative first power. So the function they gave us is exactly the same as this one here. They just look a little different. The second one, the one in blue, is going to be easier to derive. Y prime equals. So the derivative of 3x is just 3. The x will derive away. This derives to 0. Any constant derives to 0. This will derive, though. Negative 1 times the 1 that's there will be negative 1x to the next power down, negative 2. Now we don't want to leave negative exponents in our answers. So let's get that negative exponent out of there. Y prime equals 3 minus, there is a 1 in front of that, so that'll be our placeholder in the numerator when the x to the second goes down to the denominator. Now we have a couple trig functions here. It says think back here to a previous section, 1.3. We learned this as we approach 0 of sine of something over that same something. That limit is 1. And 1 minus cos of x over x here is 0 as we approach 0. These two limits can be used to prove differentiation rules for sine and cosine. The other 4 derivatives will be coming up in later sections. So these, you just got to memorize these. The derivative of sine x is cos x. The derivative of cos x is negative sine x. That negative has been the source of a lot of tears and frustration in calculus over the years. It is very, very easy to forget the negative. If you do it, don't feel bad, but try not to forget. Derivative of cos is negative sine. And we can add this to our constant multiple rules and our sum and difference rules to find many, many derivatives. So here y equals 2 sine x. Well, let's do dy dx equals, well, the 2 is a constant multiple, so the 2 is going to come along. And the derivative of sine x is cos x. Cos x. Derivative of sine 2x, or 2 sine x, is 2 cos x. That denominator 2, another way to look at it is just pull it out as a fraction, 1/2 sine x. All right, our function is 1/2 sine x. Our derivative, y prime. The 1/2 is a constant multiple. The derivative of sine x is cos x. Letter C, x plus cos x. Well, the derivative of y will be y prime. The derivative of x to the first is 1x to the 0, or just 1. And the derivative of cos is negative sine. So we could write it as plus a negative sine, or just minus sine x. Letter D. Ooh, one of each in there. Pi over 3 is just a constant, and it's being multiplied, so it's a constant multiple. It's just going to come along for the ride. Y prime equals. The derivative of cos x is negative sine x. And then we're going to have minus this constant times the derivative of sine is cos x. Negative sine x minus pi third times cos x. And I see a graph up in the corner. What's this? Oops. If you have some number times sine x, the derivative is going to be that same number, whatever it is, a times cos x. Yeah, because that would just make your derivative steeper at the origin. Remember, we're finding slopes here, so that would just make our tangent line steeper through the origin. Now, e to the x, if you had me for pre-calc, I mentioned that e to the x was very, very magical, and you would not experience that magic unless you came to calculus. So here, for those of you that made the journey to calculus, is the magic of e to the x. Now, I'm not going to take the time here. It's kind of a simple proof. You know, we got our f of x plus delta. There's our difference quotient. We do our e to the x plus delta x. We factor out an e to the x. And when you sub in the definition of e from our limits section, the cancellation cancels out these delta x's. The derivative of e to the x is e to the x. It is its own derivative. So it's here in Theorem 2.7. The derivative of the natural exponential function, e to the x, derives to e to the x. Now, graphically, what this is saying is, on our e to the x graph, whatever the y value is at a point is also the slope. This would be e to the 0. At x is 0, e to the 0 is equal to 1. The slope of this blue tangent line here would be 1. When we go to this point, this would be 1 comma e to the first. And remember, e is about 2.72 decimal goes on, but its height on the y-axis is also its slope. This is the y value as well as the slope. We could go way up there higher. The next point would be 2 comma e to the second power. E to the second is the height on the y-axis, and e to the second is also the slope occurring at that point, on that tangent line. So the y value is its own slope. E to the x is its own derivative. Example 9. Here we're just going to throw some e to the x's in there. We'll throw some power rule and some trig function stuff. So I'm just going to do the answers down here. A. F of x, our derivative will be f prime. And 3 is a constant multiple, and the derivative of e to the x is e to the x. So 3e to the x derives to 3e to the x. Letter B. F of x will derive, let's do f prime. The derivative of x to the second would be 2x to the first plus e to the x derives to itself. Last one, letter C. F of x will derive to f prime. The derivative of the first term sine x is cos x minus the derivative of e to the x is itself, e to the x. There's our derivatives. Now this leads into the last two examples, rates of change. You've seen how the derivative can be used to determine a slope. The derivative can also be used to determine a rate of change of one variable with respect to another. Applications involving rates of change, sometimes referred to as instantaneous rates of change, occur in a wide variety of fields. A few examples are population growth rates, production rates, water flow, velocity, and acceleration. A common use for a rate of change is to describe the motion of an object moving in a straight line. In such problems, it's customary to either use a horizontal or vertical line with a designated origin to represent the line of motion. On such lines, movement to the right or up is considered in the positive direction. Movement to the left or down is negative. And that corresponds with our coordinate axes. If we're going to the right or up, that's positive. If we're going to the left or down, that's negative. The function s that gives the position relative to the origin of an object as a function of time t is called a position function. If, over a period of time, delta t, the change in time, the object changes its position by this amount. Delta s is s of t plus delta t minus s of t. That should look very familiar. That's part of the numerator of our difference quotient. And then if we use this old formula, rate equals distance divided by time, we can get an average velocity. The change in distance, delta s, divided by the change in time, delta t. So here in example 10, let's say we're up on a 100-foot high building and we've got a billiard ball and we drop it. The ball's height at S will represent how high we are above the ground. At time t is represented by this function, negative 16t squared plus 100. Now in this one, in example 10, we're not actually going to do any calculus or take a derivative. This is sort of a setup. We're going to approach this as 2 points getting closer together. So here it says find the average velocity over these intervals. Now notice these are brackets. These are an interval on the x-axis. If here's my xy axis, I'm going from x equals 1 to x equals 2. What is the average rate of change? So what we have here, this 1 and 2 are just x values of points. I have 1 comma something, and I have 2 comma something. I need the y values that go with them. And I dragged my slide up too far. Here is my function. S equals negative 16t squared plus 100. So if I plug the 1 in there, negative 16 times 1 squared plus 100, out pops an 84. If I put 2 in there, 2 squared is 4 times negative 16, subtract or add that negative number to 100, and we get 36. So here's 2 points, and they want us to find the average velocity. So we're just going to set up a slope formula between these. I'm going to do 84 minus 36. That's my change in the y coordinates. And then I'll do 1 minus 2, subtracting in the same order. Here I did 84 minus 36. I got to do 1 minus 2. And that turns into a 48 over a negative 1. So our answer is negative 48 feet per second. That's an average. Remember, we're dropping something off a 100-foot building. So here we are on a 100-foot building. We throw off the billiard ball. Here it is after the first second. And then here is the second. What is the average rate of change over that interval? And here we saw it was negative 48 feet per second. But let's get our points closer. B, we're getting closer to 1 comma 1, or a 1 comma, yeah. We're getting close to using the same point twice, 1 comma 2, 1 comma 2. For B, we're going to do 1 again. That's still going to be 1 comma 84, but now we're going to do 1.5. We put 1.5 in the function, and we get 1.5 comma 64. So our slope will look like 84 minus 64 over 1 minus 1.5. So our numerator is a 20, our denominator is a negative 0.5, and that gives us an answer of negative 40 feet per second. So now instead of falling a full second, we went from the first second to 1.5 seconds, and we see the average rate of change, the average over the interval is changed a little bit. I'm going to start a new slide so I don't have to erase. Part C, we are going to use the same point 1 comma 84, but now our new point is 1.1 comma, and we put that in our negative 16t squared plus 100 function, and we get out 80.64. Put it into the slope, 84 minus 80.64 over 1 minus 1.1. We get about 3.36 over negative 0.1, and that turns into negative 33.6 feet per second as an average. So again, let's look at all those. We had negative 48, negative 40. We're getting closer and closer to 1 with our second point. And we're down here to negative 33.6 feet per second. Again, this is an average velocity, no calculus required, but we were setting it up to take us to this next part here. Suppose in that example, we wanted to find the instantaneous velocity, or simply the velocity at exactly the first second. Just as you can approximate the slope of a tangent line by calculating the slope of a secant line, we can approximate the velocity at that first second by calculating the average velocity over a very small interval, 1 comma 1 plus delta t. By taking the limit as delta t approaches 0, we obtain the velocity at that moment, time equals 1. Try doing this, you'll find that when the velocity when t equals 1 is exactly negative 32 feet per second. In general, if s equals s of t is the position function for a moving object on a straight line, the velocity at time t, this is going to look very familiar, v of t, velocity, the limit as delta time goes to 0, s of t plus delta t minus s of t over delta t is s prime. So this is what we've already seen, but they just changed some stuff. The variables. Instead of using f of x, we're using s of t. S for position, t for time. You know, this is going to be more used in the applied problems, in the stuff where we're modeling things in the real world. Instead of x's and delta x's, it'll be t's and delta t's. And if we take our position function and derive it, we get velocity. Position derives to velocity. In other words, the velocity function is the derivative of position. Velocity can be negative, 0, or positive. I didn't point that out in our last example. This was a negative. All of these answers were negative, and that just means it's going down. In this example, we dropped a billiard ball off a building, and the negative says our ball is going down toward the ground. Velocity can be negative or 0 or positive. The speed of an object is the absolute value of its velocity. So back to here, we dropped the billiard ball. You could say this billiard ball speed is 48 feet per second. Its velocity is negative 48. The negative tells us that the ball's headed down. If the velocity was positive 48 feet per second, that would mean that the ball had been thrown up into the air. So back to here, the position of a free-falling object, if you ignore air resistance under the influence of gravity, can be represented by this function. And let me erase and move this stuff up. So s of t, your position above the ground, is 1/2 g times t squared plus v sub o, this is your initial velocity, times time, plus s sub 0, your initial height. G is the acceleration due to gravity. On Earth, the value of g is approximately negative 32 feet per second, or negative 9.8 meters per second. We're mostly going to stick to the feet in here. So if we make this g, let me circle it in red, this g into a negative 32, and we multiply it by that half, we're going to get negative 16 time squared plus v sub o times time plus s sub o. This is our position on Earth with Earth's gravitational constant. The v sub o, this is initial velocity, and s sub 0 is initial height at which the problem begins. You will be seeing this quite a bit. So here, example 11, this is our last example. We've got a diver at time 0. The diver jumps from the platform that is 32 feet above the ground, or above the water, the ground, because the initial velocity of the diver is 16 feet per second. Think about it. The diver is on the board. He's going to spring. He's going to jump up a little bit. So he is going to have initial positive velocity. Here would be his position function. The negative 16t squared tells us we're on Earth. The positive 16 here attached to the t tells us he is initially moving up at initial velocity of 16 feet per second. And here is the height of the board above the water. So all those pieces fall into our blank position function. And now we can answer a couple questions. S is measured in feet. Time is measured in seconds. A, when does the diver hit the water? Or how could we determine when the diver hits the water? Remember, S of t is our position. Or in this case, it's our height above the water. If I put a 0 in for t, at time 0, the first term would be 0, the second term would be 0. We have 32. At time 0, we're here at the top of the diving board. We're 32 feet above the water. So how do we figure out when we hit the water? We want to set position equal to 0, because when we hit the water, we are 0 feet above the water. So set it equal to 0. Let's see here. The first thing I would do to get this under control is factor out a negative 16. So that would be t squared minus 1t minus 2 equal to 0. I would divide by negative 16, so that's out of the way. And then you factor t minus 2, t plus 1 equal to 0. If we have factors multiplied set equal to 0, that means we can set the first factor, t minus 2 equal to 0, and get t as 2 seconds. Or we can set t plus 1 equal to 0 and get t equals negative 1 seconds. Now, sometimes these problems lead to answers that don't make sense. So the question again is, when does the diver hit the water? Well, he either hits the water 2 seconds after he jumped or 1 second before he jumped. So that's obviously our nonsense answer. You can't hit the water before you jump. So here is our solution for part A. When does the diver hit the water? 2 seconds after jumping. Part B. What is the diver's velocity at the time of impact? Well, let's see. We have a position function, negative 16t squared plus 16t plus 32. If we take the derivative of s, that would be s prime. And another name for s prime, the derivative of position, is velocity, v of t. And we'll derive with the power rule. 2 times negative 16 is negative 32 times t to 1 power lower, and then plus the 16t will derive to a 16, and the 32 is a constant that derives away. So here is our velocity function. How do we find the velocity at the time of impact? Well, we know the time to impact is 2 seconds. So we need to find v of 2. What is our velocity at the moment of the second second? Negative 32 times 2 plus 16. That's what, negative 64 plus 16, or negative 48 feet per second. Negative means we're going down. There is a little bit of time, very, very early in the problem that we would actually have a positive velocity. Like if we put in 0.1, we would get a positive velocity because our diver would still be bouncing up on the diving board. Yeah, that's it for that example. And odd problems, that's it for that video. I'll see you in the next one.